Okay. Can the audience hear me? I got a little bit disconnected from what's going on. Yes, the audience can hear me. Great. Okay, so welcome to another session of FHPNC, our last one with regular presentations. For our first presentation will be by Adam Paske on parallelism-preserving autodiff for second-order array languages. This was one I've been looking forward to myself. So here we go, Adam, the stage is yours.
Yeah, thanks a lot. Yeah, sorry, the title is a bit of a mouthful, but yeah, anyway, thanks everyone for coming. So today, yeah, we've basically been exploring sort of some new avenues in array languages, and one of our specialty, both for me and my co-authors, is working with automatic differentiation. That's the autodiff part of it. We're all at Google Research, and thanks for having us here. So just to start with, most of you are probably aware with what I'm going to say in the first few slides, but just to better motivate sort of the landscape of what's out there and what's not out there. If you really just go to I don't know, if you start Googling for array languages, what you find most people use is something like MATLAB, or one of the really whole explosion of Python-based sort of DSLs for array computing, and most of those really look very similar. The basis of them is something like you have a whole bunch of basic math ops. Then you might have, for example, a few hard-coded reductions, you'll have probably plus, times, max, and minimum. And then you will have some other operations which could be expressed as compositions of those, but are included for efficiency. For now, I also set aside things like indexing and conditionals and loops. Those do require some other care. If you're interested, for example, in differentiating slicing, you might be interested actually in one of the in the paper that we also with the same authors actually as a subset in the main ICFP track, because we talk about it there. But so one really common property of all of those is that there are no user-defined functions as arguments. All of those are kind of, because they're usually embedded DSLs, which kind of come with prepackaged code before, and the host languages that you use to call them are usually relatively slow. You probably don't want to actually end up calling user-defined functions. Users instead are expected, if they really expect high performance, they're expected to compose their program out of the primitives that are provided. But the good part about it is that actually AD is largely solved. I mean, obviously there are extensions, and actually one of the things that we are working on is improving the stuff that's already there, but kind of the basic stuff that gets you most of the way is already there and has been there pretty much for years now. But obviously, user-defined functions arguments are really nice, and they actually enable you to do a whole bunch of interesting things. And so most of the languages that you actually find at the workshop here, they do have primitives such as map, which applies a function to a collection of things independently. You have reduce, which just combines a whole bunch of elements with a binary reduction. And you have scan, which is reduce, but except you output the element at every step. And the really nice thing about all of those is that, maps pure functions are generally always parallel, and also reductions and scans, if the binary function is associative, you can also evaluate them in parallel, which makes them a really good basis for, for data parallel languages, for compilation to GPUs, right? And so this is really the scenario that we're interested in working with, and this is kind of the language that we've defined in our paper. It's really just roughly lambda calculus here at the top. Then you have the array combinators with map, reduce, and scan being kind of the main ones. The rest ones are first order, so kind of they're less interesting from AD point of view because we already knew how to do those things. And then there are sort of special combinators for AD purposes, and this is what I'll be talking about a bit later. But so we all know that this is a nice basis. Something like a matmul is really just a composition of two maps and a reduce. But the benefit is that once you start code generating, you can actually do other semi-rings, and you just expand a lot. So just because it's so worthwhile, just because everyone here probably has interests and is working in something like those languages, we figured out that actually looking at how AD behaves, and also we're working on similar languages, so figuring out how AD behaves on such languages was just an interesting challenge for us. So before we get into what works and what doesn't, let's just quickly look at what AD actually is. So generally, we will be working with functions from some A to B. And if the function is differentiable, for now, we will assume that all functions are differentiable and that all of the types, both for inputs and outputs, are vector spaces. So just to recap, actually, the properties that I need for this presentation are there's like a 0 element, which is a neutral element of addition of things. And so if A and B are vector spaces, okay, for simplicity, they have to be vector spaces. In reality, they can be something else. But the derivative then is a function with a very similar signature, except you do append, you do kind of duplicate the input argument. And the semantics of this are, well, if you evaluate f, you have to give it a point and you get some output. And derivative is similar. Derivative still needs to know around which point it is supposed to work. But then once you give it a point, it also needs kind of a delta, like a change in the input space, right? Which is, let's say, a nudge, a small nudge you might apply to the input. And what it will output, the derivative function, is not the actual output of the function. It'll actually output how, like, if you nudge the input by the second argument, what is the expected, kind of what is the approximate change you will see in the output argument, right? And just to kind of put this all together, all of this is summarized with something like a first-order Taylor expansion, where, again, if you have function f and you nudge some x by an epsilon, where x is the first argument and epsilon is the second one, what you get out is the value of that function plus kind of the change that the derivative function estimates. Or, because, so that was kind of, sort of, hand-wavingly, I explained the semantics of what this is supposed to be. But if we are to reify this actually as a programming language function, it looks something like this. You have, for forward mode, AD is one of the two modes. We actually do like to call it JVP for Jacobian vector product, because that's kind of what it corresponds to semantically. And so it is actually a function transformation. You can give it a differentiable function as the first argument, and what you get back is another function, which actually takes as input, you take the x and you take the sort of sensitivity, the perturbation on the input, and what you get out is the output of the function and the sensitivity of the output to that perturbation. It's just more efficient oftentimes to just evaluate them together, which is why the signature looks like this. So okay, so that's kind of roughly what, that should give you some idea of what AD is supposed to be computing, and that is forward mode AD. We'll also get to the other mode of AD a little bit later. So what are the AD systems that we do have today? So the stuff that we know already is, well, we know how to do automatic differentiation of languages that are, of array languages that are first order, where you have no kind of user control, because then, well, you have just a finite set of primitives that you have to handle, and you might need to extend it a little bit to have primitives to express the derivatives. But usually, at some point, all of those languages kind of reach a fixed point where you have a language which is closed under differentiation, and you can compute like arbitrarily high derivatives. And if you have just something like 4 reductions, you just sit down with pen and paper or some symbolic tools, and you can just work out what the derivatives are. Then there are systems that could handle something like second-order languages, but they do not work on as high level as the SOAC programs. So a good example here is something like Enzyme, which works on the level of LVMIR. So it's essentially, AD for kind of low-level sequential languages with sequential semantics, and what you get out the derivative, again, is sequential semantics, right? So most of the languages that we talk about here probably will lower to some step to a similar language at some point, but we might want to do AD a bit earlier, simply because it gives us more flexibility to do optimizations than this late. We know that scans, we know that reductions have some nice properties, and we might want to use them. We might want to also apply those nice properties to do optimization on the code that AD produces. So just dropping this far down might already be somewhat unacceptable. Interestingly, there are also other systems which can handle something like second order, so arbitrary, user-provided kind of monoids for reductions, but they do require extra static knowledge about array sizes. It's essentially, the idea is that if you, for example, know the array, the size of the array, and if you know the user-specified function, this might already be enough information for you to pick some strategy of actually evaluating those, something like a scan. And so you can just unroll this strategy because you know exactly how many elements there are, so you can just unroll the program, and then you can differentiate through this kind of like a first order, right? So essentially, you can normalize your second order program into a first order program, roughly, if you have this extra information. But this doesn't always hold. In particular, in the language that we're interested in, DEX, we do not want to assume static knowledge about array sizes. We do not want to unroll those things before AD. And so roughly the goal that we want here is that the AD rules of map and scan should involve just map and scan. Another nice property of having something like this is that, well, if the derivative of map is another map and the derivative of scan is another scan, then your system hopefully will also be closed under differentiation. And again, you not only support first-order derivatives, but also arbitrary order derivatives. Also, I will not be really talking about reductions, simply because, well, you can see a reduction is a scan post-composed with like a projection of the final element. And so, just for simplicity and for the sake of, conserving time, you can just view it as like a special case. OK, so how do you roughly implement AD systems? What you do, one nice thing about sort of derivatives is that we have the chain rule. And the chain rule is essentially a theorem that says that if you have two differentiable functions and you compose them, then it's also differentiable. And the derivative of the whole of the composition is some expression that involves the derivatives of the individual elements. And so the nice thing about this is that it is actually sufficient to just specify the sort of rules for how you differentiate language primitives. And then from those, you can inductively build up the derivative of larger programs through this composition rule. And so really our task here, the second one is nothing new. This is well known, and every AD system does this. So really what we have to do is just specify rules for the language primitives. And in particular, we do know how to do things like differentiating first order array programs. So really the interesting cases here will be map and scan. Case of map, fortunately, is fairly simple. Again, kind of calculus 101 is if you have a bunch of elements and you apply, if you have a vector of a few elements and you apply a function kind of component-wise to this vector, then the derivative also is computed component-wise by taking the derivatives of every individual function. So the rule for map is fairly simple. If you have a map of f over x, then to compute kind of the sensitivities and the outputs, what you do is you map the JVP of f over the arrays x, and kind of the x prime is like the epsilon, the kind of nudge, the perturbation to x's that we're propagating as we're computing the derivatives. So now the question is, what do we do with scans? This is a little bit more involved, mostly because the biggest issue that you really find when you do this is the JVP of f. If f is associative, right, because we assume that about the binary functions that we give to scan, then JVP of f is not just straightforwardly associative, really. If you take the associative law, right, so for all x, y, and z, this equation holds. The for all is important because this means that in particular, it is valid to just differentiate both sides of this equation. You get something like this. And so this looks very similar. This is a kind of like an associative law on those perturbation variables. So if x is the some point we're interested in, x prime is the perturbation we're applying to x, then this looks very similar to an associative law on the perturbations. The only caveat here is that we have those. Oh yeah, sorry. Actually, one thing that I should have mentioned is, so those derivative functions, they have two inputs, but I kind of treat the second input, the perturbation, as like a more important one when talking about derivatives. And also, I will indicate this in a notation where the first argument is applied in the subscript, and the second argument is applied kind of using the mathematical function application notation. This is also kind of this is also because you can view the derivative as like a family of functions that is indexed by the points in the input domain. And so this really selects one. This x really selects one of the derivative functions, in this case around x, and we can then keep evaluating that function around with different perturbations. So, the notation here essentially says that if you take a derivative of circle dot, you can instantiate it at some points for its both arguments, and then you can apply it to some two sensitivities to get the sensitivity of the output. And so, getting back to this pseudo associativity law, you can see that it's really not full associativity because the four functions we have here are four completely different functions, because the indices, the sort of members of the family of of the derivatives of circle dot, we just select 4 completely different ones because the primal points that we have in subscripts are completely different. And so, it's not immediately clear how to do this, but really it's not super complicated either. You can just do kind of the classic trick of, once you have just bundle some extra information, and in particular, if you just take pair the values with their sensitivities, like if you take pairs of x and x dot, you can write out like a circle plus operator, which just applies circle dot on the first one and then applies the derivative on the appropriate points, propagating it through the second component, and you can actually prove that this is associative. It's not super difficult. You just use this pseudo-associativity rule, and it all ends up working out. This is kind of the expression you can use to differentiate a scan. It doesn't end up being too bad. So, okay, so I guess this is roughly what it takes to do forward mode differentiation. I guess at this point you might be wondering, why is this even a paper? But this is not where the problems end. So now that we have AD, one thing that we would really like to do is run gradient-based optimization. That's kind of the workhorse of AD. That's like really what powers most of machine learning. Roughly, the idea is that if you have a function from some A, which might be, I don't know, an array of billion floats that are parameters of some optimization problem, and that outputs a single scalar, which kind of indicates how well you're doing, you would like to extract gradients of that function. So given any input, you would like to kind of figure out what is the direction of the steepest descent, for example, in the function, and then kind of use this as a heuristic to move in the parameter space in the direction locally in the direction of the steepest descent, hopefully reaching some local minimum. But the problem is that if you look at JVP, if our function is from some A to a scalar, if we substitute the scalar for a B, kind of a simple type-driven proof, not even resorting to mathematics, basically indicates that if you evaluate JVP, you can only get at most 1 or 2 scalars out of it, right? And the gradient in particular, if you have a billion parameters, should have a billion elements, right? So you will have to it is possible to reconstruct the gradient using JVP, but it will have to evaluate it repeatedly, and in particular, many, many times, which is obviously not desirable if you have a large neural network or something. So there's an alternative formulation to JVP, which is linearize. So given a function, you can actually get back it kind of unzips the both parts. So if you apply linearize to a function, you get back another function, which takes the same input and gives you the same output, plus the derivative function, which is not evaluated immediately. You kind of get it back. And what's important is I use this funny arrow to actually indicate that it's a linear function. It's not just any arbitrary function. All derivatives are linear functions, which is actually really important, because linear functions have transposes. And transposes are really nice because they let you swap out the sort of domain and codomain. And so in particular, we would like to have something called VJP. So JVP is Jacobian vector product. VJP is actually vector Jacobian product, which is just like linearize, except we kind of swap this one, swap the order of the arguments to this function. So if we could transpose it, in particular, it is possible to do it. If you implement VJP, you can just compute the gradients using a straightforward expression, and then you're done, right? So given that forward mode wasn't that difficult, it shouldn't be too hard, right? And it turns out that it's actually a nightmare. Those are the rules for scan and reduce, and I don't know. It was difficult to work them out. I actually implemented them once to just make sure that I didn't actually end up having some typos in here. But it's definitely not satisfying. So this is way too complicated. This does not feel like the right solution for this, even though it is a solution. It does not feel like it's really a right solution just yet. And also, what's even kind of, I don't know, what's silly is that it doesn't even have the right asymptotics. There's a nice theorem in AD community which says, I don't know, we often like to call it cheap gradient principle, which basically says that in your programming language, if you take all programs for any there is a constant that is independent of the program that you pick, such that the cost of evaluating the something like a JVP of f or VJP of f is at most that constant of the cost of evaluating f, right? And the issue is that this system doesn't even satisfy this. There is somewhat a nice bound you could derive, which is something like the sort of nesting scans in the binary reductions of other scans blows up this constant, and as deep as you nest, you can blow up this constant as much as you can. So it's not like I would assume that those are relatively exotic programs, so it's not that big of a deal, but it's still somewhat unsatisfying that we can't satisfy this, because other AD systems generally do satisfy the rule. So, I'm diverging from the paper at this point, but I just want to give you just to finalize, I just want to give you an outlook on what we think about what we should do as next steps, but this you will not necessarily find in the paper. So both JAX and DEX, which are the systems that we're working on, decompose reverse mode AD into 2 steps, into linearized that you actually saw before, which is kind of forward mode. And then there's another transform, which is transpose. So it's not like VJP as an atomic unit. VJP is actually implemented in terms of those as a composition of 2 other sort of program rewrites, which actually separates the concerns and makes them much easier to think about. The question is, can we apply this to SOAC languages? And for reductions, I think I worked out a relatively OK thing. But it turns out that for scans, it just doesn't seem to apply that nicely. Basically, scans just seem like a really weird primitive from the AD point of view, where the sort of AD system ends up fighting with the compiler, which is way too much control over there are so many different ways to reassociate the expression that AD would like to have some visibility into this. But at the same time, we don't want to constrain the compiler too much, because that is the beauty of scan being so high level, right? So what if scan is really just the wrong level of abstraction for something like differentiation? Just to give you a sort of very rough estimate of what is the issue, what AD does is when you have some operator, like the green box here, some operator with 1 input and 2 outputs, but you can see that it could lower it to some other operators inside. Really, what you're doing when you're differentiating is when you do reverse mode, you kind of construct a very similar program, except the data flow is reversed. This is why it's called reverse mode. But the problem is that there are actually additional data dependencies that cross from those inner operations of the primal thing into the sort of data flow graph, let's call it, of the reverse mode derived program. And if we're talking about scans, we don't get to necessarily make up arbitrary outputs, right? Those might be some intermediates that are hidden in the implementation of the scan. We don't get to output them. But we really would like to have those arrows for the sake of efficiency. But because we can't have them, the best thing we can do is we end up just recomputing some things that we compute for the function while we compute the derivative. And that is roughly, I think, what ends up causing the blow up in complexity of the programs. And the reason that we can't have those arrows is what prevents us from nicely decomposing the sort of reverse mode differentiation into linearization and transposition. So really, the kind of research question, I guess, that follows from this paper is what is the highest level language that still has the nice properties of abstraction of the SOAC languages, but still admits nice and cheap AD? So in summary, in the paper, we do outline how to do forward mode and reverse mode, or JVP and VJP, of SOAC programs. But the VJP is both really complicated and not even as efficient as you could probably make it up. So we do actually, I think, have a language that satisfies this. We just didn't actually have time to write it up properly. But if you're interested, we're happy to talk about it. But so yeah, essentially the follow-up is to just try to come up with some different way to formulate a scan, a different signature for it, or maybe as a composition of some other primitives, and then try to decompose the monolith of VJP, which just ends up being really complicated, into linearization plus transposition, which hopefully should make it both easier to think about the problem and fix the inefficiency issues. All right, so I think we still have 5 minutes for questions, so seems like a good place to stop. Thank you.
We have some questions. I'll put the first question on stage. Would defunctionalizing scan help?
Right. I think it would. That is roughly what I was hinting at when I was, assuming defunctionalization. How would you defunctionalize a scan? Defunctionalizing a scan probably means that it just expands its implementation and inline the function or something like that. And that is roughly this point, right? Where, yeah, it would, but you do have to commit to an implementation before AD runs. And it's not always possible to commit to a single best implementation right ahead of time. So yeah, and this is how, for example, JAX implements user-defined associative scans and reductions. But I still wouldn't consider it a full. I wouldn't consider it AD for SOAC programs, because you still have to lower the SOAC program into a first-order program.
So I will follow up with a small question. So scan doesn't, if you just worry about the asymptotics, then you don't need scan as a primitive. You can write it as a sequential loop, a map, and a scatter. You need some kind of scatter then.
Right.
Are those more susceptible to reverse mode AD then?
Yeah, good question. Well, map certainly works perfectly well, and scatter also shouldn't be too bad. I mean, the question is, what happens on something like right conflicts? But yeah.
But in this case, you would actually know it's a nice, well-behaved scatter, no conflicts, no overrides. It's kind of
if you decompose it that way, then yeah, that could work. I mean, if you have a good efficient implementation of scatter that would be competitive with something like the scan algorithms, then I think that should work. I haven't thought about implementing scans that way, but if that's a good idea, then sure, that could be one way of working around this.
Well, the keyword here was asymptotically optimization.
Right. Yeah. Exactly. So yeah, that's what I'm thinking about. So we're really interested in differentiating the fast stuff and not just the asymptotically fast stuff.
Well, the next question is actually mine. So, is there a similar proof that you talk about the proof that reverse mode only adds a constant overhead? But is there a similar proof that reverse mode even preserves the parallel asymptotics in principle?
That's actually a great question. I haven't thought about this, and I haven't seen a proof. One thing that so basically AD is funny because pretty much everything about AD has been worked out like in the 80s, but not AD on parallel languages, which is like the niche that I think has still a lot of gaps. And so I will not guarantee you that this proof doesn't exist, but I haven't seen it, and it might be a fun thing to derive. But I expect that if you work out, I mean, if you can express the derivative of something like a map as a map and scan as a scan, then I guess it should preserve the parallel asymptotics as well. It might just be a constructive proof of something like that, right?
Yeah, I think the big question is that when you're gathering together all of the that's an accumulation, so that's a reduction in general, and that has logarithmic span.
Sorry,
when you are reversing the data dependencies, what was once many uses of one value, which we say is constant span, becomes an accumulation of many values into one, a reduction, a summation, which has a logarithmic span. So my hunch would be that from the parallel asymptotics will be a logarithmic factor worse.
I mean, yeah, there you go. So I guess the answer is no. I mean, you can just differentiate a program which broadcasts a scalar, right? And there you go. Like, it doesn't preserve it.
Right. But then the question is that logarithmic dependency?
Yeah.
And you might argue also that broadcasting being constant span is maybe also not really reasonable for a large enough machine.
Right.
Okay. Okay, so there are no more questions from the audience, so I will ask one more. This language that you mentioned that you're working on that handles this better than in the paper, is that language just DEX?
Sorry, which language that handles? Right. Yeah, this was heavily inspired by DEX because we've added. So previously, DEX only supported reductions with like 0 and plus as being the monoid because that's what we really want for AD. I mean, we've added this for the sake of AD, but we ended up just using it in a bunch of places in just user space. Like we wanted to write programs with this and with arbitrary reductions. But then the problem was I had to write an AD rule for this, and I had to figure out like how to differentiate arbitrary reductions, and it didn't seem like people have been doing that. So this was really the thread. But yeah, it was very DEX motivated, and even though DEX is not combinator oriented, I just figured that since the DEX paper only has been published like in ICFP on this track, it just seemed better to frame the problem as differentiate of SOAC languages, and they're so close that it's really almost the same problem, I think.
Yeah. Well, thanks again for a nice presentation. I'll give you a little bit of applause again, and then
thank you.
I'll kick you off stage and make room for the next speaker.
Cool. Thank you.